Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So today we are going to cover the last part of this chapter, name name dual nature of radiation and matter. So we are talking about the failure of wave theory of light to explain photoelectric effect. So what are the reason responsible for the failure of wave theory of light? Because we know that photoelectric effect is explained with the phenomenon of particle nature. Clear? Photoelectric effect explained by the particle nature, because in that we have considered light is made up of the very small energy particle and particle of energy, and this particle of energy for a light is called photon. Means light is made up of photon. So Huygens wave theory of light could not explain the photoelectric emission due to the given reasons. So these are the point we have on that. This uh, wave theory of light is unable to explain the photoelectric effect. First, according to the wave theory of light, if the intensity of the light is increased, there will be an increase in amplitude of the waves, and hence energy carried by the waves will be increases. Yes, according to the wave theory, we know I is proportional to amplitude ka square, and am amplitude refers to the energy. Means if you increase the intensity, there will be increase of amplitude, and amplitude is directly related to energy, so energy also increases. Clear? And hence any energy carried out by the wave will be increased. But what happened? We know we have increased this energy, and there is we have increased the intensity. There is no change in the kinetic energy. Previously, we have studied this one by using diagram. Yes. See, by increasing intensity, there is no change in stopping potential. Obviously, there is no change in kinetic energy. Clear? So, actual situation is different from that predicted one. So when the beam of light falls on a metal surface, the energy carried by the light is distributed uniformly over the entire surface of a metal. All the free electrons present in the surface of metal will receive the light energy, and they will be ejected out of the metal surface. When the waves of the light of higher intensity fall on the metal surface, it will impart more energy to the electrons in metal, due to which the kinetic energy of the ejected electrons will be increases. Yes, what happened? When the waves of light of higher intensity fall on a metal surface, it will impart more energy to the electron in a metal, due to which the kinetic energy of the ejected electron will be increased. This is against the experimental fact. Yes, this is against the experimental fact. Okay, that the maximum kinetic energy of the ejected photoelectron is independent of the intensity of incident light. Means what we assume? We assume this one, but this is not the correct thing. Okay. Okay, so this is against the experimental fact. Experimental fact are not as the thing is given here. Okay, the maximum kinetic energy of the ejected photoelectron is independent of the intensity. Okay, second point of failure. According to the wave theory, by increasing the intensity of incident wave of light, the energy can be increased and photoelectric emission will takes place even if frequency of the incident light is less than the threshold frequency. Yes. So, by the wave theory, if by increasing intensity you can uh, increase amplitude, and by increasing amplitude you can have a greater energy, it means you can fetch out the electron just by increasing the frequency. No way. There is a concept of cut off limited frequency. This is called threshold frequency. Okay, no matter how much intensity you are giving, but if the photon having an intensity less than V naught, this is threshold frequency, there is not a single electron can fetch it out. Okay. But it is against the experimental fact that no photoelectric emission will takes place from a metal surface if the frequency of the incident radiation is less than the threshold frequency, no matter whatever be the intensity. So the observation is just opposite to the predicted one. Clear? Okay. Next, third point. When a wave of light falls on a metal surface, the energy of the wave of the light will not go to a particular electron in a metal, but it will be distributed to all of the electron present in the illuminated portion of metal surface, as a result of which the electrons will take some time to accumulating the energy required for their emission for metal surface. Yes, this is according to the wave theory. Wave theory said that when a energy falls on some metal, okay, uh, only not a single electron take all the energy. Rather, this energy is distributed on that surface. Okay, on that surface. Yes, energy of the wave of light not go to a particular electron in a metal, but it is distributed all the electron present in the illuminated portion. Means in the illuminated portion, this energy is distributed. Okay, as a result of which electron takes some time, because this energy will travel up to some distance. Then after the electron take will after traveling taking some time, suppose this electron get fetched out, means there is a time lag. There is a time lag for fetching out of electron. Clear? Yes. But what happen? This is also against the experimental fact that the emission of the photoelectric electrons takes place immediately. What we have seen, there is immediate ejection of electron. Okay, after the light is incident on the plate of metal. Done. Okay, so our next topic is dual nature of radiation. Student, till now we have read that radiation can have its wave nature, and second, radiation can have also its particle nature. Okay, radiation is of particle nature, but student, now we have to realize the symmetry between these two natures, that a particle nature and a wave nature. So who observe this about the dual nature? That is de Broglie. Okay, the radiation sometimes behaves as a wave and sometimes as a particle. So hence the radiation having dual nature. So radiation is supposed to be having a dual character. In a particular experiment, the radiation has a particular nature. Yes, means at a single time, when you observe radiation as a wave, then you cannot realize as a particle. Clear? Means in a particular experiment, the radiation has a particular nature. Either you will feel wave nature or particle nature. Clear? The various phenomena related to the radiation can be divided into three categories. Yes. First point, the variation phenomena related to the radiation can be divided into three categories. First, the phenomena like interference, diffraction, and polarization, etc. These phenomena can be explained on the basis of electromagnetic wave nature of light. Yes. So these three phenomena are strictly can be explained with the help of wave nature only. Got it? What phenomenons? Interference, diffraction, and polarization. Second, the phenomenon like photoelectric effect, Compton effect, etc., can be explained on the basis of quantum theory or particle theory only. Okay? Only. Third, the phenomenon like rectilinear propagation, this is called reflection or refraction, etc., can be explained on the basis of either the wave nature or the particle nature of the radiation. Clear? So these phenomena can be explained by both. Even uh, Isaac Newton explained by the corpuscular theory. So reflection and refraction well explained by the particle theory as well as wave theory. Got it? Yes. So now we are talking about de Broglie dualistic hypothesis. So what Max Planck said? Max Planck said that radiation having a particle character or quantum character. So this is about radiation. But de Broglie said that there is a wave associated with the particle, and de Broglie calculated the wavelength of this wave. Okay, means the wavelength of the wave that is made up of the particle. So simultaneously with momentum, that is the particle character, de Broglie calculated the wavelength of the particle, wavelength of the wave, that is equals to h by p. Clear? We are going to derive this one. So de Broglie calculated this one. Okay. So this is called de Broglie dualistic hypothesis. Okay. So let us derive. We have to derive this uh, wavelength of a wave. So according to de Broglie, a moving material particle sometimes act as a wave and sometimes act as a particle. Or you can say there is always a wave is associated with a moving particle. Means there is a particle. Hmm. If a moving particle is there is a wave is associated with this moving stream of particles, and this wave is called matter wave. This wave is called matter wave. According to the de Broglie, a moving material particle sometimes act as a wave and sometimes act as a particle or a wave is associated with the moving particle. The wave associated. Yeah. So or a wave is associated with a moving particle. The wave is associated with a moving particle is called matter wave. Yes. Means if you're talking about ourselves, like we are moving here in some place, we are going, okay, we are as a particle, and if we are going with some speed, we having some mass, okay, then there is a wave associated with us, and this wave that is connected with the moving particle is called matter wave. This wave is called matter wave. So this wave associated with the moving particle is called matter wave or de Broglie wave, whose wavelength can be called, whose wavelength is called de Broglie wavelength, and it is given by lambda equal to h upon mv. Okay, so lambda equal to h upon p. P means momentum. So write this formula. This is called de Broglie wavelength, lambda equal to h upon mv. Okay. What is m? M is the mass of the particle about which you are talking. Okay, for the existence of de Broglie wave. And v is the velocity of the particle. And h is here Planck constant. And de Broglie wavelength lambda equal to h upon mv. Means what we observe here? Mv is the particle characteristics and lambda is the wave characteristics. So actually you relate here the particle characteristics with the wave characteristics. Clear? Lambda equal to h upon mv. Next topic, derivation of the de Broglie wavelength. So we have to derive this de Broglie wavelength lambda equal to h upon mv. Okay. Yes, matter wave. So we have to derive the wavelength of this matter wave according to the Planck quantum theory. What Planck said that every radiation is made up of the particle of energy that is called quantum. Okay. According to Planck's quantum theory, the energy of a photon of a radiation of frequency nu is given by the relation E equals to h nu. So give it equation number 1. Mm. Okay, here photon of the light is considered to be a particle of mass small m. Yes, particle of small m. Then accordingly to the Einstein mass energy relation, the energy associated with this particle is given by E equal to mc square. Yes, this is the energy connected with the photon equal to mc square. So first is equal to h nu equals to h nu, energy of the photon by Planck quantum theory, and equal to mc square is the energy of the photon by using Einstein relativity. Clear? Okay. By 1 and 2, so if you relate here h nu and mc square, so h nu becomes mc square or m becomes h nu upon c square. Clear? So this becomes mass. This becomes mass. Now you know the momentum of the photon. Momentum of the photon equal to P equal to mass into velocity. So here mass equals to h nu upon c square and velocity becomes c. Now you cancelled here. Okay. So 1c is cancel here. Now here it is h nu upon c. We know that the formula c equals to nu lambda. C equals to nu lambda. Clear? So nu upon c it becomes 1 upon lambda. So it is equals to 1 upon lambda equal to nu upon c. It becomes 1 upon lambda. So h into nu upon c, because can be written as h upon lambda. So this is momentum p equals to h upon c. Clear? Sorry. Lambda. P equal to h upon lambda, or lambda equal to h by p. Clear? Lambda equal to h by p. If a particle is moving with a speed of v, then lambda equal to h upon mv. H upon mv. So this is the formula for wavelength. So de Broglie assumed that the above equation equally applicable to both the photon of radiation and other material particle. Okay, so no need of this line, only we have to write till lambda equal to h upon p, that is equals to h upon mv. Okay, students, question is here. An electromagnetic wave of wavelength lambda. First wave की जो the wavelength of the wave is given by lambda is incident on a photosensitive surface. So here is a wave that incident on a photosensitive surface of negligible work function. Means work function is almost zero. Okay, means the energy of the wave will converted into the what, kinetic energy, means half mv square. Why? Because we know the formula that E equals to h naught plus k max, E equals to phi naught plus k max. When phi naught equal to 0, this total energy will convert into the k max. Clear? If the photoelectron emitted by the surface have a de Broglie wavelength of lambda 1. Yes, this is of emitted electrons wavelength. Photoelectrons emitted from the surface is having the wavelength lambda 1. You have to prove that lambda is equals to 2mc upon h. Means what you need to do? You have to find the value of the emitted, you have to find the value of the incident wavelength. Okay, what wavelength has incident there, you have to find this value lambda. Okay, so by the Einstein energy equation, what you have, you know, E equals to h nu equals to phi naught plus k max. Now h nu equals to hc upon lambda. Okay, lambda is the incident wavelength, equals to phi naught is 0 here, and this k max become half mv square. Okay, k max equals to half mv square. But convert this half mv square in the form of momentum. So use the class 11th formula. So we have the formula k equals to kinetic energy, k equals to half mv square. Clear? We have the formula from 11th class, k equals to half mv square. You can write it k equals to 1 upon 2. You can multiply m in the numerator, so it will become m square v square. So mv whole square. As you multiplied in the numerator, so you have to multiply in denominator m also. So k equals to mv whole square upon 2m. Okay, so k becomes equals to p square by 2m. So this is the value of kinetic energy. In the terms of momentum, k equal to p square upon 2m. Also, k equal to p square upon 2m. Then p square becomes 2mk. So one more formula for p. P is equal to under root 2 mass into kinetic energy. So mainly we have two formulas here. K equal to p square upon 2m. Clear? Okay. So there we have hc upon lambda equal to k max. So this k becomes p square upon 2m. So on putting p square upon 2m, now momentum we have equal to, by this solving this, you will have the momentum p equal to 2mhc upon lambda. This is the value of p equals to 2mhc upon lambda. Now de Broglie wavelength connected with the particle is given by lambda equals to h upon p, where p is the momentum of the particle. So we got the momentum of the particle here equals to lambda equals to h upon, so de Broglie wavelength of the particle. So particle of the wavelength is there lambda 1. So lambda 1 equal to h upon p, and we have p is equals to 2 mhc upon a small lambda. Clear? 2 mhc upon a small lambda. Now 1 h and h, this get h get cancelled out. So you have lambda 1 equals to, see here, this h square root lambda upon under root 2m h into c. You can write this h as a product of 2 under root h, and 1 h will cancel out. So lambda equals to lambda 1 equals to small under root lambda upon under root 2 m c. Clear? Yes. So squaring both the side, on squaring both the side, you will have lambda is 1 square equals to lambda upon 2mc. Oh, one more h will be there. I've just forget. So I written here. Now, after squaring, it will be there. So the relation lambda equals to now 2mc upon h multiplied by 2mc upon h multiplied by lambda 1 square. Clear or not clear? So this is the wavelength. De Broglie wavelength for an electron. Students, this is important formula for only numerical purpose. Okay, de Broglie wavelength of an electron means here electron is moving. Okay, so if electron is moving, it will constitute some wave. You have to find the wavelength of this electron. Okay, so by the relation kinetic energy of the electron is equals to half mv square. Half mv square. If you controlled this electron by applying some negative potential at anode with some voltage V naught. Yes, here this is electron, and you have applied a stopping potential V naught. So half mv square becomes E into V. V is the potential. Clear? Yes. By potential difference D, you make the electron accelerated from rest. From okay, so half mv square equal to EV. Yes. Then half mv square equal to EV. So V becomes V. Velocity of the electron becomes small v. M v square equals to 2 EV. So v square equal to 2 EV by m. So v equals to under root 2 EV upon m. Okay. So this is the value of E v. Now for the formula lambda equal to h upon mv, just place the value here. You will get h upon under root 2m because 1m will be cancelled. This is the formula for wavelength for electron. Write this one. Only this is important for numerical purposes. Lambda equal to h upon under root 2m e and v for voltage, not for velocity. V for the voltage or potential. On putting the value of remaining terms, you will have final value for the wavelength lambda equals to 12.27 upon under root voltage angstrom. Okay, students. So here an electron is accelerated through a potential difference of 100 volt means applied potential here it is equals to 100 volt. What is the de Broglie wavelength associated with it? Means you need to find the lambda. So here the particle electron is given. So for electron, for the wavelength is equals to lambda equal to 12.27 upon under root V. Make here in the place of V voltage equals to 100. So your answer will be 1.227 angstrom. This is this angstrom wavelength value comes under the spectrum of X-ray. Okay, so the wavelength belong to the X-ray part of the electromagnetic radiation. Done. Next question. The ratio between the de Broglie wavelength associated with the proton accelerated through a potential of 512 volt and second alpha particle means you have to find the wavelength ratio first for proton and then for alpha particle. Okay, then for alpha particle. Remember here the formula of electron cannot be applicable because here for proton and alpha particle. So charges are different. So some another formula will be applied there. So accelerated through a potential of 512 volt and alpha particle accelerated through a potential of x volt is found to be 1. Okay, means the ratio here is found to be 1. Then you need to find the value of x, means what is the operating voltage for the alpha particles. Clear? You need to find the value of x. So student, first we have to talk the concept involved here. First, energy is given in the form of potential. So we know that the electrostatic energy, that is U, is equals to E equals to Q into V. So here the charge, suppose the charge is Q and it is potentialized by V volt, then your energy equals to Q into V. Clear? Second case, potential, P is equals to momentum equals to under root 2 mk. Momentum P is equals to under root 2 into m into k. Okay, and this kinetic energy is gained by the application of this potential energy. So in the place of k, you must write E. So P is equals to under root 2 m mass of particle multiplied by E. Now place the value here. P equals to under root 2 m QV. Got it? So this becomes the momentum. So P is equals to 2m QV. Now, wavelength of the particle associated with this particle, moving particle, lambda is equals to h upon P. We have this is called de Broglie wavelength. So lambda equals to h upon under root 2 m q into V. In the place of EV, only there is one change. There should be EV, QV. Clear? So this is the formula, general formula for any of the particle. Lambda equals to h upon 2 mqv. Now, so lambda equals to h upon 2 mqv. H is a constant, so you can write lambda equals to 1 upon under root mqv. Now, two situations are there. One is for proton and one is for lambda. Okay, so lambda proton upon lambda alpha. Check here. All these three quantities are inversely proportional. Okay, so make a root there. Now, if alpha is in denominator, so here it will be m alpha, q alpha, and v alpha, alpha particle. And for proton, there will be m proton, q proton, and v proton. Clear or not? Yes. Inversely proportional relationship. Now, what is given here? The ratio between the de Broglie particle associated proton and alpha particle. We know the proton having the mass 1h1 and alpha particle having the mass 2he4. So the ratio of the mass will be equals to 4:1. So alpha to mass of proton equals to 4:1. So you must place here 4:1. Now Q of alpha and Q of proton. Alpha is the double positively charged particle, 2he double plus 2he4. The nucleus of helium atom is called alpha. So it is equals to the charge of 2 electron will be there. So Q alpha is equal to charge of 2 electron. And proton having the charge of 1 electron, E and E getting cancelled out. So Q alpha upon QP becomes 2:1. Fine. Now potential is given for alpha particle there is X, and for a proton there is a potential of 512 volt. Yes. So, and the ratio for the wavelength is equals to 1. Now if you're solving, you will get x upon 64, because 8 4 to the 8x upon 512 will be there inside the root. So this 8 will cancel for 64 times. So it is equal to x upon 64. Now 1. So 1 is equals to under root x by 64. Squaring both the side, 1 becomes x upon 64. So x equal to 64 volt. Clear or not? So you will have x equal to 64 volt. Next question, students. Show graphically, show graphically the variation of the de Broglie wavelength lambda with the potential V. Yes, for an electron. So same formula will be applied there. Lambda is equals to h upon under root 2 mev. Variation we have to see is V versus lambda. So clearly lambda is inversely proportional to under root of V. Okay, clear? So there is a relationship. If V increases, then lambda will be decreases. So this like will be the relationship. Okay. So lambda is inversely proportional to V. This is the graph between de Broglie wavelength and electric potential V. Done. Okay, students, check the next question. The two lines mark A and B in given figure shows a plot of de Broglie wavelength versus 1 upon under root V. Yes, you know, students, lambda is equals to h upon under root 2 m q v. Okay, lambda is equals to h upon under root 2 m q v. So here V is the accelerating potential for two nuclei, 1h1 and 1h3. Okay, so on taking here these quantities constant, you will have a graph between lambda is obviously lambda is inversely proportional to 1 upon root v. So one quantity is 1 upon root v and another quantity is lambda, then v y is directly proportional to x. So there is a straight line graph. Fine. Now the two part nuclei are there, 1h2 and 1h3. What does the slope of the lines represented? Means what does the slope of the lines represented? First thing. Second, identify the lines corresponding to the nuclei. Means which line will represent 1h2 and which line will represent 1h3. Two questions are there. Solve this. Okay, students. So we have this one formula. Y is equals to lambda is inversely proportional, sorry, directly proportional to 1 upon v. So you just check lambda here equals to, if you separate here, h upon under root 2 mq into 1 upon under root v. Okay. So this quantity becomes a constant. Okay. So lambda is equals to constant k times some 1 upon under root v. Clear? So this whole quantity becomes some constant. And this constant is what? This becomes the slope because when v is equals to ri, so v upon I becomes r, e upon I. This is what? This is slope of the vi graph. So here the quantity k, what is k? K is equals to under root h upon 2mq is become a constant. So the de Broglie wavelength of a charged particle is given by this. So the slope of this line represent what? Slope of this line represent h upon under root 2mq. Understood or not? Yes, because this is in y-axis and this is in x-axis. So this becomes the slope. By the equation of line, we have y is equals to mx. So m is called slope of the line. Okay, the coefficient is called slope of the line. Second question, which graph will correspond to 1h1 and 1h3? Remember, 1h3 having higher mass. And for a higher mass, there is a less amount of wavelength. So here the wavelength for the B is less. This means this represent for 1h3 and this represent for 1h2. Clear or not clear? Okay, so for 1h2 and 1h3 having same charges but mass are different. So lighter mass, that is 1h2 representing by the line for the greater slope A. Similarly 1h3 by the line B. Got it, students? Yes. Next question, students. Determine the de Broglie wavelength for a proton. Yes, of whose kinetic energy is equal to the rest mass energy of an electron. Okay, mass of a proton is 1836 times that of electron. It is given for a help that mass of a proton is equals to mass of 1836 times of mass of electron. Okay, so you need to find what? De Broglie wavelength for a proton. Do. Okay, student. So first part we have given, determine the de Broglie wavelength of a proton for a proton whose kinetic energy is equal to the rest mass of energy of an electron. Means kinetic energy, rest mass energy means k equals to by Einstein equation, mass rest mass is given by m naught in c square. So this is the kinetic energy. Okay, for a proton. Now, for a proton, energy, mass of the proton is equals to 1836 times of mass of energy. So in the place of m naught, you can write 1836 times mass of electron into c square. So let us derive the de Broglie wavelength. We know lambda equal to h upon p. So h upon under root 2 mk. Yes, we have derived this one today. Lambda is equals to h upon 2 mk. Sorry, p equals to under root 2 mk. So place here the value, we get h upon under root 2 mk. Now, according to the question, kinetic energy of the proton equal to m electron multiplied by c square. Proton into ce square. Sorry, here it should be kinetic energy kinetic energy for proton is equals to m proton into c square. Yes, here it should be proton. M proton into c square. By Einstein relation, m into c square. Now, H equals to what? It is H upon under root 2 into m into 2mk. 2mk. So in the place of k, put here mec square. Okay, mec square. M into c square. Here it should be proton. Now we know that the proton is 1836 times of mass of electron. So if you place here the value of m proton is equals to 1836 times of mass of electron. So by combining these two electrons, one is mass of electron and one other one is mass of proton. So you will have me outside c square. So we'll make a c outside and root 2 and it is equals to 1836. On simplifying it, you will get the value of lambda. This equals to 4 into 10 to the power minus 14. And this region of electromagnetic spectrum is X-ray. Okay. So second part here, in which region the electromagnetic spectrum does this wavelength lie? So this wavelength lies in a region of X-rays. Done?